Most cyber attacks focus on shattering a database firewall. Broken access control is different. An attacker doesn't need to force the lock if the system is designed to swing open at a light touch. To understand how these flaws are exploited, we will analyze the mechanics of lateral movement, vertical escalation, and the professional testing methodologies used to verify these vulnerabilities in production environments. The problem lies between two processes. First, authentication. At this checkpoint, the system verifies your identity and password. The second is authorization. The flaw occurs when the system fails to ask what you're allowed to do, granting access to anything. When developers fail to separate identity from permission, the database defenses are bypassed. The server treats an unauthorized request as a legitimate instruction from a trusted user. We begin with horizontal movement. This occurs when an attacker accesses data belonging to another user who has the same level of privilege within the system. In a typical scenario, we log into a standard account and navigate to our own profile page to observe how the application handles data requests. Many applications use a unique identifier in the URL to pull specific records. By manually changing our user ID from 8801 to 8802 in the address bar, we test if the server validates the ownership of that ID. If the server processes this request and returns the private email, address, or files of user 8802, the access control is broken. This insecure direct object reference proves the application confirms an active session exists, but it never checks if that session is authorized to view the specific object being requested. Vertical privilege escalation is more targeted. This involves moving from a standard user role up to an administrative role by exploiting logic flaws in the application's hierarchy. One method involves intercepting the DNS sent during a routine settings update. We use a proxy tool to pause the request and examine the underlying code. Within the JSON body of the request, we may find a field defining the user's role. By changing this value from false to true, we are attempting to promote our own account permissions. A second method is forced browsing. This relies on using automated fuzzing tools to identify administrative directories that are not linked on the public-facing website. By testing a word list against the server, we can discover hidden paths like /admin or /API delete. If these pages load for a standard user, the application is failing to restrict access to sensitive functions. These exploits succeed when developers rely on security through obscurity, assuming if a link is hidden or a parameter is invisible in the browser, a user won't interact with it. Metadata manipulation targets applications that store role-based data locally on the user's machine, often within cookies or session tokens. We can use the browser's built-in developer tools to inspect the storage tab and view the active data assigned to our current session. If the application uses a cookie to track roles, we can manually edit the value. Here, we change customer to superadmin directly within DevTools. When the server relies on this client-side metadata to determine access, it effectively allows the user to define their own level of permission without any server-side oversight. To verify these flaws without the risk of false positives, security professionals use the two-account test. This method provides definitive proof that authorization logic is failing. We set up two isolated sessions. Account A is the attacker, account B the victim. The attacker generates a private request, like viewing an invoice, captured before reaching the server. Next, we swap the session cookie, placing the victim's token into the attacker's request. We now send the modified request to the server. The packet contains the victim's identity, but asks for the attacker's specific data record. If the server returns account A's data to the session owned by account B, the authorization logic is broken. This provides the verifiable evidence needed for a security audit. We have now mapped the primary vectors for authorization failure: lateral IDOR, vertical parameter tampering, and client-side metadata manipulation. When access controls are broken, the structural security of the application dissolves. The strength of the server's encryption matters little if the software is designed to grant access to anyone who simply knows the correct URL. These techniques should only be utilized on systems where you have explicit written permission to perform security testing. Logic flaws are often more difficult to detect than standard exploits because they involve the application working exactly as programmed, but without proper checks. Subscribe for more technical breakdowns of web vulnerabilities and find tool links in the description.